Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.2.3. What we're going to be doing is taking a permutation like this. So this is 1 goes to 2, goes to 3, goes to 4, which goes back to 1, and 5 just goes to itself. And we're going to be rewriting it in terms of little switches. First switch 1 and 2, that's a permutation. Then just switch 1 and 3, that's a permutation. And then just switch 1 and 4, keep everything to else just going to itself. That's another permutation. If you do this one, then that one, and that one, so this one, so 1, 2, 1, 3, and 1, 4, and put them together and straighten them out, we actually get this 1, 2, 3, 4, and 5 going to itself. We didn't write down 5 going to itself. So up here we mentioned that we can write this permutation either as this or this. Oftentimes it's customary when we have one cycles just to not write them down. But we write down all the other cycles when we do cycle notation for a permutation. So this is kind of fun. We can take a permutation right here and rewrite it as a set of switches. Okay, first do this one, then that one, and that one. And notice and we go from right to left because this is composition of functions. First do this function over here, then that one as we go along. And we can actually read this in the following way, where we kind of think about, okay, so let's read this guy right here. If we read it, it tells us on the right that we go, where does 1 go? Well, 1, we put it in here, goes to 2, and we take 2 and it doesn't go anywhere else. So we just know 1's going to 2. Then we say, where does 2 go? So we put 2 in here, and notice 2 goes to 1. And then where does 1 go? Okay, go to the next one, guy. 1 goes to 3. And okay, then that's it. So we know 2 is ultimately going to 3. Now where does 3 ultimately go? So 3 goes in here. This fixes 3. Over here, this takes 3 to 1. And over here, this takes 1 to 4. And we're done. So that goes to 4. Now we put 4 in. Okay. This fixes 4. So 4 stays the same. This fixes 4. So 4 stays the same. You go to this one, and it changes 4 to a 1. So it goes back. Thus, we have a cycle. So that's kind of one way we can read this notation and rewrite this in terms of a cycle notation, which doesn't, where we don't have cycles that share numbers. See how all these cycles share a 1. This is not disjoint cycle notation because of that. Disjoint cycle notation means there's no cycles that share. Here, there's only 2 cycles and neither of them share. So this would be disjoint cycle notation. So we can rewrite a permutation into disjoint cycle notation in the following way. Notice it's customary to just ignore and not even write down these composition symbols, but just write the cycles right together. And it's understood that we're doing composition reading from right to left. Okay. Now notice, though, kind of what's happening. We're taking this 1, and then we just kind of read this off. See 1, and we have a 1 in each of these. And see how we're reading it right this way? So 1 goes to, well, if we read this way, it's not really read that way, but we're just kind of reading it. 1 goes to 2. It's like 1 goes to 2. And 1 goes to 3, the next guy. 1 goes to 3. 1 goes to 4. 1 goes to 4. This is actually a nice way of taking something like this and rewriting it as a string of compositions. You take your first guy and then just kind of going in this order. 2, 3, 4, 2, 3, 4, just kind of reverse it when we write this down. So likewise, we could take a cycle like this, a 5 cycle, and write it in terms of 2 cycles, which we call transpositions. So first we have 1, 2, then we'll have 1, 3, and 1, 4, then 1, 5. So 1, 2, 1, 3, 1, 4, 5. And you can check it out and make sure that works. So as 1 comes in, it goes to 2, and 2 has nowhere else to go because all the other guys fix 2. So 1 goes to 2. Now let's put 2 in. See, 2 comes in and 2 goes to 1. All right. Then the next guy over here, what does it do with 1? It takes it to 3. And we come over here. Oh, that fixes 3. That fixes 3. So we're left at 3. Okay, now we put 3 in, see what happens. Put 3 in. This fixes it. Okay, 3. Oh, that changes it to 1. Oh, this takes 1 to 4. Okay. It fixes 4. So we're left at 4. So gone to 4. Then we see where 4 goes. 4 comes in. Oh, this fixes 4. Oh, come then fixes 4. Oh, this changes 4 to 1. Okay, then the next guy takes the 1 to the 5. Great. Now we know 5 has nowhere else to go but 1 because everything else is gone to 2, 3, 4, and 5 already taken up in the codomain. So 5 better go to 1. We can check it. This fixes 5. That fixes 5. That fixes 5. Oh, that takes 5 to 1, just as desired. We close it off, and we have our cycle. So we can use the same kind of idea of splitting things up in order to write any cycle at all as 2 cycles. And so in general, if we have any permutation, so like 1, 5, 2, 3, say 3, 4, even if we did like 3, 4, 6 or something like that, we can rewrite this in terms of 2 cycles or in terms of transpositions. Let's first rewrite this one. Okay, we can write it as 3, 4, and 3, 6. See what we did? We took the first guy here and went 3, 4. That's what happens first on the right. And 3, 6. That's what happens next over here. So with compositions, remember, we do the one on the right first, then that one. Okay, now over here, we think, okay, 1 and 5. And then we can go 1 and 2. Like that. Okay. So we can take any permutation at all and rewrite it in terms of 2 cycles. Notice these aren't disjoint, and that's fine, but it still is made up of switches. So just by switching in succession different things, we can get to really any permutation at all. Okay. So let's keep going here. All right. So, all right. In particular, notice that a 5 cycle can be made up of 4 switches. 4 cycle is made up of 3 switches. Every time we have a switch, it makes 1 crossing. So we can think 1 crossing, 1 crossing, 1 crossing. So we add them up, there's 3 crossings. Hey, the number of switches is kind of like, well, 3 total crossings in the stacking. But remember that the number of crossings in the stack, like when we're looking at this, when the total number of crosses in a stack is has this exact same property of being even or odd as the result over here. So let's even count them. Like, we have 1, and then here we have so in this we have so this arrow crosses these 2, so that's like, so that would be like, so it crosses once and then it crosses twice, and then of course but then this arrow crosses this other guy another time, so that's kind of like 3. So we have 1 and 3, and then here we have 1, 2, 3, 4, 5. We have 5. So 1 plus 3 plus 5. That's okay. So we have 1 plus 3 plus 5, which is 9. So that's odd. So we have an odd number of crossings, and then we come over here and count them. 1, 2, 3. That's an odd number of crossings. So each time we have a 2 cycle, it's like you're adding an odd number. So you may as well just add the simplest odd number that you can think of, 1, because in the end, that's really all that matters between adding evens and odds. It's just its property. So why don't we just consider just adding 1s? So really, instead of adding crossings, we could just add transpositions, these 2 cycles. We could just add the number of these, and that's kind of, it'll have the same property of evenness or oddness, which is called parity. The parity of a number, whether it's property of being even or odd. And it'll have that same property as number of crossings. So here, so we would have 4 crossings. Here we'd have 3 crossings, we could say, or it's equivalent to that, even though it's not, it's a lot more crossings than that perhaps, but the same as evenness or oddness. So we see there's 3, so we could say odd. So there's an odd number of crossings. Here we see there's 4, so there's an even number of crossings. Now, it's often, and as it's written in the text, is a permutation is called odd if it has an odd number of crossings, or now we have another way of saying it, odd number of transpositions. So an odd number of transpositions in its decomposition, and it's even if it has an even number of transpositions in its composition, or an even number of crossings in that diagram, or an odd number of crossings. It's the same idea. So we often call those odd transpositions or even transpositions to mean which chunk they're actually going into on our merge that preserves composition into 2 fibers. So one chunk is the odd permutations, the other one is the even permutations. Okay, so this is how we can tell that a transposition is even or odd, is simply by looking at the number of these cycles, which we can actually get, notice, just from this as well. So you think, notice 4 splits into 3, a 5 splits into 4. So it's kind of like you take each cycle and you subtract 1, and then if you had another cycle, so let's take a look at that. What if we had something like, for instance, like 1, 5, 4, 6, and they don't even have to be disjoint. 1, 5, 4, 6, 1, 3, 2, and 5, 6. And let's just kind of take a look at this. So from this one, take 1 less, that's like a 3. This one, take 1 less, that's like a 2. 1 less, it's a 1. So I'm just counting how many numbers appear in each cycle. 3 and 2 and 1, let's add them together. And we end up getting 6, which means that this guy is an even permutation. And we found that even without even splitting it into 2 cycles, because we knew that the number of 2 cycles that came from this guy would have been 3. The number of 2 cycles that would have come from this one was 2. This is a 1 cycle in itself, so it's 1. We just added the number of 2 cycles, the number of transpositions. 3 plus 2 plus 1, we got 6. Since that was an even number, and that means it must have been an even number of crossings here after straightening, so hence it was an even permutation. So we can get that simply by just looking at the cycle, like at a cycle notation, even if it's not necessarily disjoint, and be able to see if it's an even or an odd permutation. Okay, and we will end right there. Thank you so much for watching.